So these last two sections of the chapter are not as long. They really just have like a concept or two in each of them. This section, um, section 7, we're going to look at the elasticity of demand. And so this is going to help us to measure the sensitivity of demand to any small increase in price. And economists use this to calculate that elasticity of demand. Okay. And so our elasticity of demand is denoted with the capital letter E there. And it's given by the function in terms of the price of X, right? So that's saying the elasticity given a particular X is really just negative X times the derivative of our demand function divided by our demand function, okay? And so then theorem 11 there gives us 3 different things. So if our total revenue is increasing at those X values, for which, so you'll see that the E of X is less than 1, then we can say that that is inelastic. Okay. And if E of X is greater than 1, that means our revenue is decreasing at those, and we'll say that that is elastic. Okay. And then if E of X is equal to 1, that's where we are maximized. Okay. And then we'll look at a couple of examples for this. And then you guys you'll see in a little bit when we do the exam review, you can expect to see one of these on the exam as well. Okay. So here we are, given that D of X, that's our demand of X, is 500 minus 2X. And we want to determine the elasticity of X equal to 57. Okay. And so for this problem, so when you look in the book, it's on page 351. First, it wants us to determine the elasticity. Then we're going to look at the elasticity at the given price point, which here is that E equals 57. X equals 57, and determine if it's elastic, inelastic, or maximized. And then finally, we'll want to tell when is the total revenue maximized, right? And so we can do total revenue as maximized when our elasticity function is equal to 1. So that really just means that it is maximized when our numerator is equal to our denominator. So we can set those equal to each other and solve, and that will give us the price point of where we are maximized. Okay. So first, in this one, we want to, let's do our the elasticity equation, right? And so first, to do that, we need to know what is our derivative. So our derivative in this case would just be -2. So our elasticity function is going to be -x d prime of x over d of x, right? And so now we know these parts, right? We don't know x, but we know the rest, right? So -x, my derivative is -2, and my d function, it was given to us, is that 500 minus 2x, okay? So we need to simplify. So -x times -2 is positive 2x divided by 500 minus 2x. You can see we have a 2 in every single one of these terms. So we're going to just factor out a 2 from every term. When we do that, that leaves me with x 250 minus x. So that is going to be my elasticity function. Okay? Any questions? So that's part A. Part B then wants me to substitute in that given price point. So we were given x equals 57. So let's substitute that into our elasticity equation. So E of 57 is equal to 57 divided by 250 minus 57. That reduces to 57 over 193. That is less than 1, so it is inelastic. Okay? Questions? Okay, so the third part, again, we're just setting our numerator equal to our denominator. So that is, our numerator is equal to our denominator. So that is x equals 250 minus x. Okay, so that would give me 2x equals 250, divide both sides by 2, and I get that x equals 125. So that means the revenue is maximized when the price is $125. Okay, any questions? All right, let's look at a practical example. So for this one, we're looking at the demand for oil. And it says, suppose that you've been hired as an economic consultant concerning the world demand for oil. The demand function is given here, and we're looking at x's from 0 to 180, where that is where Q is measured in the number of barrels of oil per day and at X dollars per barrel. Okay, so we want to find the elasticity. Then we're going to look at the elasticity at these various different price points, $45, $60, $75. And then we will look at where our revenue is maximized. Okay. So the first thing that we want to do, again, is take our derivative. Okay, so the derivative of our function then is going to be 150 minus 8x. Okay, our elasticity function then would be this negative x times my d prime. D prime is 150 minus 8x divided by my actual function, which was that 35,000 plus 150x minus 4x squared. Okay. And so we'll distribute the negative x to both terms in our numerator. So that's going to give me, I'm going to write the 8x squared first minus 150x divided by our 35,000 plus 150x minus 4x squared. When we simplify that, we get 4x squared minus 75x divided by 17,500 plus 75x minus 2x squared. So essentially, we can see that there is a factor of 2 in all of those terms. Okay, so what we did was we factored out a 2 again, right? So if you are factoring it out, it has to be in all of the terms, and you can factor it out. You could have written this in one more step where you factor a 2 out and made the numerator something like 2 parentheses 4x squared minus, or not 4x squared. Yeah, 4x squared minus 75x. And then the denominator, factor out a 2 out of all of those. And then you would see that the numerator and the denominator each had a 2 that canceled out with each other. But we're at a point that we're far enough along in the math level that we can probably just say, oh, every single one of those terms had a 2. So I can factor that out without that intermediate step. Okay? Questions? Okay, so part B is asking us to use our elasticity function and look having a price point of $45 per barrel. So we will evaluate our function at that then, right? We have 4 times 45 squared minus 75 times 45 divided by this 17,500 plus 750 times 45 minus 2 times 45 squared. Okay. And that is going to simplify to 0.28, which is less than 1. So we are inelastic. Okay. And if you recall, when we are inelastic, that means the revenue is increasing. Okay. And so why companies would find this important information to know is because when you want to maximize your revenue, right? So that's where we want our numerator to equal our denominator. And that's where the companies will be maximizing their profits. Okay. So here, let's look at if we were charged, or if the oil was $60 a barrel, right? So you plug it into the formula exactly the same way, and you end up with 0.67. Okay. Again, that is less than 1, so you're still inelastic. Okay. And then finally, they asked us to take a look at $75 a barrel. Once we hit $75 a barrel, we plug that into our elasticity formula and we get 1.42. That is greater than 1, therefore this is elastic. Therefore, that means that our revenues are starting to decrease, okay? And so we want to be somewhere between 60 and 75 is where we're going to meet that optimal or maximum revenue, okay? Which we will do in, so this was part C and this was part D. So in part E, we want to do where is our total revenue maximized. And so we would set our numerator, which is 8x squared minus 150x, equal to 35,000 plus 150x minus 4x squared. And we'll solve this out. Move everything to one side. We end up with 12x squared minus 300x minus 35,000 is equal to 0. We can reduce this, right? We can multiply all of this by 1/4. And in doing so, it's the same as dividing everything by 4. But that reduces us here to 3x squared minus 75x minus 8750 equal to 0. So it makes it a little easier for us to do. And then, because it gives us smaller numbers, right? Because you will need to use your quadratic formula here to solve this. And when you do use that quadratic formula, you will get x is approximately 67.93. Quadratic formula to factor that, and you'll get X is approximately 67.93, right? So that's saying that the revenue is maximized when the price is $67.93. And that makes sense that it has to be somewhere between 60 and 75 because that's where we've shifted from inelastic to elastic. Okay? Questions so far? So part F, right? So this says what quantity of oil will be sold at the price that maximizes revenue, right? So if our cost is $67.93, how much oil does that mean we're selling? So we want to evaluate our original function at X equal to 67.93, okay? And so that would be 35,000 plus 150 times 67.93 minus 4 times 67.93 squared. And that's approximately 26,732 million barrels. Because remember, that told us up here that we're working in, that our Q is measured in millions of barrels. Okay, questions? And then the last thing is it says in August of 2017, a barrel of crude oil was selling for $48. Can we look at the math that we've done over here on the left and determine if at this price, will a small increase in price cause the revenue to increase or decrease? Okay. And so if we're looking at this, so if we're looking at $48, we're somewhere between these two here. Okay. And so if the price of a barrel is $48, then there should be an increase in total revenue. Okay. Questions? All right. So that takes care of chapter 3, section 7. What we have left in this chapter is section 8. This section, again, like the previous one, isn't too long. But in this section, we're going to actually learn how to differentiate implicitly. Okay. And so I've listed out some rules here that I think, or guidelines, ways to help you kind of process through differentiating implicitly. So the first thing that you want to do is you want to differentiate both sides of the equation with respect to x or t or q, whatever variable it is that you're looking at. Typically in this class, it's usually either an x or a t for time. Once you've differentiated both sides with respect to x, you want to apply the rules of differentiation. And anytime an expression involves a different variable, in this case, we'll say y, then you need to know that dy dx will be a factor in the result. Okay. So you'll then, number 3, want to isolate all terms that have dy dx as a factor and move that to one side, and then factor out that dy dx. Divide both sides of the equation by whatever you need to isolate the dy dx, and that is what your derivative would be. So essentially, what we're saying now, so when we're differentiating implicitly, this means that we're going to be differentiating things with multiple variables, right? So in the past, all of the work that we've done up to this point has been taking a derivative of something that only has one kind of variable. Okay? So now we're going to look at what if I have x's and y's in the same equation, then how do I differentiate them? Okay? Question. All right. So let's look at a couple of examples. We'll do that walking through using those 5 steps that I put on the previous slide. I'll kind of talk you through them, number them out on here. So when you go back, you can kind of fill in your notes with the words from the previous slide if necessary. Okay. So the first step here, okay, so the first step that we want to do is we're going to differentiate both sides. Okay, so we're just dx of 2xy plus 3 equals dx of 0. Differentiating both sides. That's what step number 1 says. Okay. Step number 2 told us to apply the rules of differentiation as necessary. If there is a y involved, we have to stick the dy dx next to it. Okay. So let's look first at how do we take the derivative of this? Okay. That's really just 2, right? The derivative of 2, we can factor that 2 out. So we end up with 2. And then we have that ddx of 2xy plus d dx of 3 is equal to d dx of 0. Okay. Let me go ahead and make all of this back to blue. Okay. So really all we're doing is we're bringing this 2 outside and differentiating then actually, so that 2, I shouldn't have wrote that there. It should just be like this. Okay, so all we've done is bring that 2 outside of what we're differentiating. Now, this right here, I just use the product rule. Okay, so when I use the product rule for that, I have f equals x, g equals y. So my derivative of x with respect to x is 1. My derivative of y is going to be, with respect to y, is going to be 1 dy dx, right? So remember, it said anytime we differentiate with the variable other than the main one that we're looking at, we differentiate it normally how we would, but we have to tack on that dy dx as part of it. Okay. So now using our product rule, fg prime plus gf prime, okay, we're going to end up with 2x dy dx plus y times 1 plus 0 is equal to 0. Okay. So this simplifies to 2x dy dx plus y equals, actually it's 2y because we have to bring the 2 to both pieces, is equal to 0. Okay. Any questions so far? Now step 3 says isolate the terms with dy. So we have this term here with dy. We want to isolate that. So we end up with 2x dy dx And we're going to move the rest of the stuff to the other side. So that's negative 2y. Okay. We can divide both sides by this 2x because what we're supposed to be doing in step 4 is to factor out a dy dx. We didn't need to factor out the dy dx. So we can just say this here is step 3, and we can skip straight to step 5 because the dy dx is the only term, so we don't need to factor it out. And so when we divide both sides by this 2x, we end up with dy dx is equal to negative 2y divided by 2x, and that simplifies to negative y over x. So the derivative then of 2xy plus 3 is really negative y over x. Okay, questions? So I will put here a little note that, so just something to keep in mind, the derivative of y with respect to x is dy dx. Okay? All right. Questions? So this is number 18 in our textbook. That comes off of page 359. And so this problem is asking us to differentiate implicitly to find dy dx and then find the slope of the curve at the point that was given. Okay. So for this one, we will do the same steps, right? We're going to first differentiate both sides of the equation. So first we're going to differentiate both sides. So d dx of 2x squared minus 3y cubed equals d dx of 5. Okay. So that actually becomes d dx of 2x squared minus d dx of 3y cubed equals d dx of 5. Okay. So the derivative of this first element, that becomes 4x, right? 2 times 2x. Actually, I'll write that out here just so to help visualize, so we can bring that constants out to the front. The reason I'm going to do that is to help you see it with the y. So this is really 2 times, and then the derivative of x squared is 2x. Minus, we bring the 3 out, take the derivative of y cubed. The derivative of y cubed is 3y squared. But remember, that's a y, so we have to add on the dy dx. Okay? And then the derivative of a constant is 0. Any questions with that? Okay? Let's simplify. So this gives me 4x minus 9y squared dy dx equal to 0. So now I want to isolate, right? So when I want to isolate, this is like step number 3. So this was step number 2. We applied the rule of differentiation. Step number 3, we're going to isolate. So to isolate, we have this, we can minus 4x from both sides, right? That gives me negative 9y squared dy dx equals negative 4x. Okay, still working on isolating here. So we can divide both sides by negative 9y squared. Okay, so this gives me dy dx equals, we have a negative and a negative, so that gives me positive 4x over 9y squared. Okay, so now that we've isolated, we've got that, we want to find the slope. Okay, so we're going to find the slope of the tangent line to the curve. We have the point -2, 1. So we have dy dx is equal to 4x over 9y squared. So that is 4 times -2 divided by 9 times 1 squared. And that gives me a -8 over 9. So that tells me that the slope of the curve, or the slope of the tangent line to my curve, is -8/9. Okay, questions? Let's look at another example that's a little bit more involved. So for this one, we have, again, first we want to differentiate both sides. So we have d dx of xy minus x plus 2y equals d dx of 3. Okay. So let's just break this out. That's d dx of xy minus d dx of x plus d dx of 2y equals d dx of 3. Okay. So this first one here, that means we're going to have to use the product rule. So my f is equal to x, my g is equal to y. So my f prime equals 1, and my g prime equals 1 dy dx. Okay, so if I use my f g prime plus g f prime, that will give me x dy dx plus y times 1. Okay, now we'll carry that down over here. So that gives me, so this whole thing here is this whole bit here. So that is x dy dx plus y. And that's all in parentheses for that piece. Okay. Then we can work the other piece when we take the derivative of x, right? That's just the -1. When we take the derivative here, this one, we can pull this 2 to the outside, right? And so that's going to give me plus 2. And when I take the derivative of y, that is, the derivative of y is 1, but then I have that dy dx. Okay? And then the derivative of a constant is 0. Okay, so let's go ahead and just simplify this, clean it up a little bit. So we end up with, we don't have to have the parentheses on this, because the only reason we would have needed a parentheses is if that had like a negative in front that had to be distributed to both terms. It doesn't, so we can leave it like this. And now we can combine up any like terms. We can see that this term has a dy dx and this term has a dy dx. So let's go ahead and say, if I factored an x out of the first term and a 2 out, or if I factor the dy dx out, I'm left with an x plus 2 dy dx. And then what's left is the plus y minus 1, okay, is equal to 0. Let's move. Remember, we're needing to isolate. So let's move minus y plus 1 to the other side. Okay. So that will give us x plus 2 dy dx equals negative y plus 1. Now we want to isolate the dy dx, right? So we will divide both sides by this x plus 2. Okay. And that gives me that dy dx is equal to negative y plus 1 over x plus 2. Okay. And the last thing we need to do then is to find that slope. Okay. And so finding the slope at that point, negative 5 2/3. Okay. That gives me dy dx is equal to negative 2/3 plus 1 minus over minus 5 plus 2. And so that's going to give me a positive 1/3 over negative 3. So that's the same as saying 1/3 divided by negative 3. That's the same as saying 1/3 times the reciprocal, which is 1 over negative 3. And so this slope would be a negative 1/9. Okay. Questions? Okay. The last example out of this section and out of this chapter is an applications problem. And so this one is, if you have cells of a self-help book called I Can Differentiate, T weeks after it is published is given by this function here. After how many weeks is the rate of change of cells maximized? Okay. So remember, to find the maximum rate of change, you want the x coordinate of the point of diminishing returns. So what I will tell you is there is a section in the textbook that says to solve this problem, we'll need to use the point of diminishing returns, which is defined by, so point of diminishing returns and so that is really just our ln of c divided by r at L over 2, okay? And so, and that's at the first and the first derivative, right? So our first derivative is LCR e to the negative RT. So you can see that's kind of along the lines of that PERT for continuous compounding. All right, so what are all these letters, right? So in this example that we're looking at, we can see that L is equal to, so kind of along this, our L is equal to this 75 or 750,000. Our C is equal to 355. And our rate is equal to this 0.07. Okay. So if we want to find the maximum rate of change, part A, then our X is equal to ln of C over R, which is ln of 355 divided by 0.07. And so that's approximately 83.89. Okay. And so after about 80, almost 84 weeks, the rate of change of cells will be maximized. Okay. So part B asks us, what is the rate of change of cells at the time found in part A? So what we want to do for part B is we want to just rate of change. Remember, rate of change is derivative. So we will apply that here. And so our derivative is going to be our function here. So we have our L, which is the 750,000 times 355 times 0.07 APR, e to the negative interest rate of 0.07 times the 83.89. Okay. All of that, though, still has to be divided by the denominator there of 1 plus 355 e to the negative 0.07. T is the 83.89. And all of that is squared. Okay. So when we do that, using your calculator, of course, we get 13,125. So the rate of change at about 84 weeks is 13,125 books per week. Okay. So part C wants to know how many times has the book been purchased at the time that we found. So that's just plugging that back into our original equation. And so we get F of 83.89, and that's going to be the 750,000 divided by 1 plus 355 e to the negative 0.07 times 83.89. And that's going to give us a value of 375,000. So that tells me that the book has been purchased 375,000 times after the 84th week. Okay. Questions? All right, so that is all of the material from chapter 3. What I will say is we'll take this 10-minute break. We'll come back and we will do the chapter 3 exam review for next, the exam that you guys will have next class period. Okay, so it's 7:44. So let's just come back at 7:55 p.m. Okay. Come back 7:55 and go over the exam review. All right, it is 7:55, so let's go ahead and carry on with the exam review. So, exam 3 will be this coming Monday. You will have the usual 100 minutes to complete the exam. And like all of the other exams, you do have to show your work in order to receive any credit for the problems, except for there will be like one or two. And as we go through the review, I will point those out, the ones that don't actually need work to be shown. There will be 6 problems on the exam that are worth 10 points. There will be 8 problems on the exam that are worth 5 points. And you'll see on this review, I've written out how many points each exam is worth. And then in addition to that, I've also, you will be able to see that on the exam as well. So you don't have to memorize or guess. It'll say this problem's worth 10 points or this problem's worth 5. Okay. All right. Any questions before we get started? All right. Give me just a second. Okay. So the first problem that we have here, this is going to be worth 10 points. Okay. And so for this one, this is where you're out of section 3.1, you'll want to be able to tell, let me turn to that page and get you what the exact instructions are. So this is out of 3.1. Page 277 of your textbook. And this one is really just wanting you to determine any critical points and any relative extrema. Okay. So for this one, the first thing you want to do is take the derivative. So our h prime of x is going to be 3x squared minus 12x minus 15. Our derivative is exists for all numbers in the domain, so we can set that equal to 0. So 3x squared minus 12x minus 15 equal to 0. That will give us, we could factor a 3 out of both sides. And so if you divide everything by 3, right, that gives us x squared minus 4x minus 5 is equal to 0. Factor that out. We get x plus 1, x minus 5 is equal to 0. So our critical points are -1 and +5. So we want to evaluate our function at those critical values. So our function would be the -1 cubed minus 6 times -1 squared minus 15 times -1 plus 1. And that will give us a value of 9. Okay. We evaluate for our other critical point of 5. So this gives me 5 cubed minus 6 times 5 squared minus 15 times 5 plus 1. That gives me a value of -99. Okay. So the last thing we want to do is let's look at our maximums and minimums, right? You can refer to page 268 for that table if you're still looking at that. You may not have that table, though, accessible on the exam. So you'll need to make sure you can do this without referencing to that. So let's build this out. We have our test value that we need, our derivative, and then what is the result of that. And then we have 3 intervals, right? Because we have two critical points. So this is negative infinity to our first critical point, which is -1, then -1 to our next one, which is 5, and then 5 to infinity. So test value wise, we can choose a -2, a 0, and a 6 here. When we do that, we end up with our derivative is 21, which is greater than 0. So we're increasing. The next one, if we plug 0 into our derivative, we end up with, just trying to pull it here so you can see the derivative. So we're looking at plugging it into this equation here. When we plug the 0 into that, we end up with -15, which is less than 0. So we are decreasing. And then lastly, when we look at the value of 6, we get 21, which is greater than 0. So in this place, we're increasing. Okay. So what we're looking at here is this is a negative, right? And when we're going from increasing to decreasing, we have that maximum here. Okay, so that maximum occurs at this point, this critical point here of -1, and then the value is that 9 that we evaluated. Okay, similarly, when we're looking at the negative values, okay, this one is our most negative. That occurs when we go from decreasing to increasing. We have that minimum. That minimum occurs when our x is equal to 5 and our y value is -99. Okay, so this right here is really what's going to be looked for on the exam, right? So what point do we have a maximum and what point do we have a minimum? Question. Okay. This next one, this is like number 34 in the textbook. It's very similar to the previous problem. However, it's asking us to find any relative extrema, list each extrema along with the x value at which it occurs, identify the interval over which the function is increasing and over which it's decreasing, and then sketch out the function. Okay, so I will tell you on the exam, if you do not label your graph, you will not get credit for your graph. Okay, unless you do it on graph paper, and I will assume that every box is equal to 1 as long as you don't put any labels, right? If you put a label, then it is what you put. Okay, so taking the derivative first, we have f prime is equal to -1 minus 2x. So we can set that equal to 0 because our function is differentiable on that there. So we have f prime equal, well, not f prime. We have -1 minus 2x equal to 0. So x is equal to -1/2. Okay, so we only have one critical value. So let's go ahead and we have negative infinity to -1/2 and -1/2 to infinity. So our test value, our derivative, and then our result is what we need to build on this table. Test value for the first one, we'll use -1. The second one, we'll use 0. When I plug that into my derivative, I get 1, which is greater than 0. Therefore, I am increasing. When I plug 0 into my derivative, I get -1, which is less than 0. Therefore, I am decreasing. Okay. So I am going from increasing to decreasing. So in this case, I'm going to have a max. Okay. And that is going to occur at the point, well, we have to calculate that, right? So if I know my x is negative 1/2, so I need to evaluate my function at negative 1/2, and that would be 5 minus negative 1/2 minus negative 1/2 squared, and that's going to equal 21/4. Okay, so we'll have this max point. It occurs at negative 1/2 and 21/4. Okay, so the last thing that we need to do is graph our function. And so in this case, let's just plot us a few points. So we have our x value and our f of x value. We already know that negative 1 is going to be a point, so let's put that on here. We have negative 1/2. Let's do a couple above it and a couple below it. So when we plug those values into our original function, we would get 3, 5. We calculated this as 21/4, which is approximately 5.1 for graphing purposes. This is 5 and this is 3. So when we have to graph that, if you have graphing paper and you don't label it, we'll assume that this is a 1, this is 2, this is 3, this is 4. Okay? So we'll go -2, +3, put a point. -1 up to 5, put a point. -1/2 up to 5.1, put a point. 0, 5 point, and 1, 3, we have a point. So our graph looks something like this. Okay? Question. This problem is worth 10 points on your exam. Okay? This next problem, you will not have any work that you have to turn in. So what it's looking for here is where are we concave up, where are we concave down, and what is our inflection point. Okay, so you can see the graph is flowing here, and somewhere about right here is where it's going to start transitioning to going concave down like this. And so where you have that breakout point, right? This point right somewhere around right here, that's called our inflection point. And on the exam, you'll have an actual graphic picture that you'll be able to get a clearer picture of versus the sketch that I've done here. But so this one would have an inflection point of 2, 2. Okay. So then everything to the left of that, my graph is concave up. Everything to the right of that, my graph would be concave down. And so we just write that interval. So -infinity to 2, and then 2 to +infinity. Okay, questions. This one's worth 5 points. Okay, this next one worth 10 points. This comes out of section 2 in your textbook. This is on page 291 and number 14. So the instructions ask us to give the coordinates of any critical points and determine if they're relative maximum, minimum, or neither. And then identify the intervals that it's increasing or decreasing. Give the coordinates of any inflection point, identify intervals where the function is concave up or concave down, and then sketch. Okay, so this is kind of going through that whole process that we covered in the beginning sections of chapter 3. Okay, so the first thing we want to do is take our derivative. So g prime of x is equal to 3x squared minus 48. Our second derivative is going to be 6x. Okay. So the first part, what it's asked us to do is look at the coordinates of any critical values. Okay. So let's set our derivative 3x squared minus 48 equal to 0. Okay, move the 48 to the other side, divide both sides by 3, and we get x squared is equal to 16. When I take the square root of that, I get that x is equal to plus or minus 4. Okay, so let's evaluate g of x and g prime of, g of x and g prime of x, both at 4 and negative 4. So we would have g of 4 is equal to 4 cubed minus 48 times 4 minus 1. And that will simplify to negative 129. Alexis, did you have a question? Your microphone is unmuted.
Oh, I'm so sorry. I must have did that when I put my headphone in. I'm sorry.
No, you're fine. I just wanted to make sure you didn't have a question. Okay, so now we have our g of 4. Let's look at g double prime of 4. And so that's going to give us 6 times 4 is equal to 24. While we're here, let's just do g of negative 4 and g double prime of negative 4. So that's going to give us negative 4 cubed minus 48 times negative 4 minus 1, and that will be a positive 127. And g double prime is 6 times negative 4, so it is negative 24. Okay? So what else do we need? Well, let's look at our, we can do our test there to determine, let's do that on this side here. So we'll need a test value, our g prime, and our result. Okay, so we're negative infinity to negative 4, negative 4 to positive 4, and positive 4 to infinity. Okay, so getting our test values, the smallest ones we can in each of those intervals, would lead us with the negative 5, 0, and 5. So when we plug those into our derivative, we get 27 is greater than 0, which means we're increasing, or negative 48, so it's less than 0, so we're decreasing. And then 27, which is greater than 0, so we're increasing again. Okay, so that tells me here we're going from increasing to decreasing. So we're going to have a max, and that will occur at the point x equal negative 4. So at negative 4, then our value is 127. Okay, so for this one, we're going from decreasing to increasing. So we have a minimum. We're looking at that for our x equal to 4. So x equals to 4 is negative 129. So that would be our point there. Okay. Questions so far? The next part we want to look at is our inflection points. Okay. So we're setting our second derivative, 6x, equal to 0. Since it is possible, we can see that that occurs at x equal to 0. So we'll evaluate our function at x equal to 0. So that's 0 cubed minus 48 times 0 minus 1. So that is negative 1. So we have an inflection point at 0, negative 1. So that's something that we'll need to put on our graph as well. And the last thing we want to do is determine where it's concave up and concave down. So we'll use that inflection point as our interval now. So that is going to go from negative infinity to 0 and 0 to infinity. So our test value, we cannot use 0 because it's part of the boundary. So we'll use -1 and +1. We'll test that against our second derivative. When we do that, we get -6 for the first interval, which is less than 0. So we are concave down. The second interval, we get +6, which is greater than 0. So we'll be concave up. Okay. So we use all of that information that we are given to help us graph this function. Okay. So here's a good example of not being able to use just strictly the axis, right? Because we're needing to graph -4 to and 127. So let's just call this 125. And equally, that was how many? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6. We'll make this -125. And then we can 1, 2, 3. We'll let this be 4. 1, 2, 3, -4. Okay. So first of all, we have an inflection point at 0, -1. So here's 0, here's -1, right? Because we're not quite on the axis, but there's 125 between here and there. So it's somewhere there. Obviously, I'm not gonna grade super precise. That's why it's important that you label all of your things. Okay, so that's our inflection point. Let's see, that's here. So I'll just highlight that here so that if you're come back and look at this video, you can see where that comes from. I'll write it here too, inflection. Okay, let's put our maximum and minimum on here as well. So we had the maximum at -4 and +127. So here's 125. So 127 would just be right above that. This is our maximum. And we would have had a minimum at 4 and -129. So maybe somewhere around here. That will be our minimum. Okay. And so then the graph would look, so you see we're concave down right there, and now we're going to transition and we'll be concave up after that inflection. Okay, so you can, to reiterate that again, you could see this piece is looking concave down and this piece is looking concave up. Okay, questions? Okay, so for this next problem, this one you will need to draw out here. So it gives us a bit of information. It tells us that our graph is concave up at 1, 5. So what we want to do is let's come put a dot on our map at 1, 5. So here's 1, 3, 4, 5. Here's this point 1, 5. It tells us that we are concave up at that point. So we know that we're looking something like this, right? Or it says we're concave down, sorry. So we're looking something like this. Then we want to go to the point 7, -2. So here's 1, 2, 3, 4, 5, 6, 7, -2. We have this point right here. It says that we have a minimum, so we're concave up, right? Or it says we have a concave up, so that tells us that we have a minimum. This one told us that we had a max. And inflection point is that transition. Okay, and that occurs at the point 4, 1. So we come over here, 4, 1, that's our transition. So when we draw all of that in, we know that it's coming somehow like this. It transitions, and now we're coming like this. And so it could be various different forms. What I'm most looking for on the exam, okay, so as I mentioned, it's various forms. So someone may have put something like this, right? So they could be varying different graphs. What is important is that these 3 points are exactly here. Okay. How you run your curve through those is up to you. That information isn't given in the problem. This problem's worth 5 points. Okay. Questions? Okay, so for this next one, this is out of section 3.3, page 305. So these problems like this problem number 8, it is asking you to find the vertical asymptote. Remember, to find the vertical asymptote, that is, where does my denominator equal 0? But you have to remember, you have to factor it as low as you can, because anytime there's a multiple with the numerator and the denominator, that means there's a hole in the graph potentially, and not necessarily an asymptote at that point. So let's go ahead and factor this. This will be x plus 6. My denominator is x plus 1, x plus 6. And you'll see that there's an x plus 6 in both the numerator and the denominator. So this reduces to 1 over x plus 1 over x plus 1. So I know that x plus 1 cannot equal 0. Therefore, x cannot equal to -1. So I have a vertical asymptote at x equal to -1. And I'll put here, just as a reminder, you might have a hole at x equal -6. Okay. Questions? All right. This problem is worth 5 points. Okay. This next one is going to be out of the same section. And this one has, we're looking for the horizontal asymptote. Okay. So remember, to find the horizontal asymptotes, we need to look at the limit as x approaches infinity. And so we have the limit as x approaches infinity, and we have to take the largest exponent in the denominator. So in this case, that's x to the 5. So that gives me 5x to the 4 over x to the 5 minus 2x cubed over x to the 5 plus x over x to the 5 divided by x to the 5 over x to the 5 minus x cubed over x to the 5 plus 8 over x to the 5. Okay. And remember, these all drive down to 0 because the denominator is larger than the numerator. It's a bigger number than the denominator, and then the numerator. Okay. And this one then will simplify just to 1. Okay. And so we're left with this value that is the limit is 0 over 1 as x approaches infinity. We don't have any x's to plug that into, so it just simplifies to 0. And therefore, I have a horizontal asymptote at the line y equal to 0. Okay, questions? This problem here is also worth 5 points. Okay, this one is 10 points. Quite a few moving pieces. The first one, we want to find our intercepts. So when we do f of x equal to 0, that gives me 3x minus 1 over x equal to 0. So that gives me x is equal to 1/3 when I simplify. Not negative 1/3, just 1/3. So 1 point I will point out. You must put that in a ordered pair. If you just say that 1/3 is that 1/3 is intercept, that is not true, because if you look at a graph, here's this point 1/3. If I said 1/3, that means this whole line here is an intercept, and that's not true. It's actually only where it crosses the 0 that is the intercept. Okay, so you will be deducted points if you just put x equal to 1/3, because that is not an intercept and you're being asked for the intercepts. When I'm looking at my y-intercept, we let x equal to 0. So that would be 3 times 0 minus 1 over 0. And that is undefined. So I have no y-intercept. Okay. Looking at it, our vertical asymptote and our horizontal asymptote. Our vertical asymptote is going to be x equal to 0, because that is where my denominator is undefined. My horizontal asymptote, in this case, you could see that the exponent of my numerator and the exponent of my denominator are the same. So I can just look at these here and reduce. That gives me 3x over x. So y equal to 3 is going to be my horizontal asymptote. If I have a horizontal asymptote, I cannot have a slant asymptote, so there will be no slant asymptote. Okay, any questions? So moving on to our derivatives and our domain. Our first derivative then is going to be 1 over x squared, which is x to the negative 2. Then our second derivative would be negative 2x to the negative 3, which is negative 2 over x cubed. Okay, so the domain then would be negative infinity to 0 and 0 to infinity, because remember, we have that vertical asymptote at 0. Okay, questions so far? So the last things that we have to do for this problem is our critical points. So this is, where is our derivative equal to 0? Okay, and since our derivative is 1 over x squared, there will be no critical points, because if we had critical values, we can't have them, because our when we set our function equal to 0, we get an undefined answer. So looking at the extrema, it is negative infinity to 0 and 0 to infinity. The test value here, we can be -1 and 1. Our derivative is going to be 1, so it will be increasing for the first one, and it's a 1 also for the second one, so it's also increasing. We have no critical point, no extrema, so you can see that they're both going in the same direction, and that is increasing. So we look at our inflection point, that is looking at our second derivative equal to 0. That is to say we look at that second derivative, it's -2 over x cubed. Again, we can't set that equal to 0, so we will have no inflection point. No inflection point. Okay. The last thing we'll look at here is if it's concave up, concave down, and then graph it. So when we're doing the concave, we're doing that based on the second derivative. Okay. And so our interval is -infinity 0 and 0 infinity. Using the same testing values of -1 and 1, we'll end up with the second derivative. We'll have a positive value, so we're increasing. The second one, we're negative, so we are decreasing. And so when we're increasing, that tells us we are concave up. When we're decreasing, that tells us we're concave down. And so when we come over here to plot this, we put our asymptotes in at 0. We had what? 0, x equal to 0 and y equal to 3. So 1, 2, 3. So we have our asymptotes built in here. And so on the interval from -infinity to 0 will be concave up. And on the interval from 0 to infinity will be concave down. Okay? Question. Again, just make sure you label your graphs so that you maximize the points. This next problem is coming out of 3.4 on page 314. And this one is worth 10 points. And this problem is asking us to find the absolute maximum and minimum value of each of the intervals indicated, and then indicate the x values at which they occur. Okay. So in this case, we have our derivative is equal to 1 minus x to the -2, which is the same as 1 minus 1 over x squared. And so f does not exist for x equal to 0, right? So f does not exist for, or f prime does not exist for x equal to 0. But if you look over here, 0 is not in our interval. Okay, so it doesn't matter. So we can say that if we set our derivative equal to 0, we would get 1 minus 1 over x squared equal to 0. So that is x squared is equal to 1, or x is equal to plus or minus 1. Okay, note -1 is not in the interval. Okay, so the only endpoint that we're going to look at here is x equal 1. Okay, and that happens to be one of our endpoints because remember that was -1 to 20. Okay, any questions so far? Okay. So let's look at f evaluated at 1. That is 1 plus 1 over 1, which is 2. Let's look at f evaluated at 20. So that is 20 plus 1 over 20 equals roughly 20.05. Okay. So in this case, here we're going to have an absolute minimum at x equal to 1. Here we'll have an absolute max at x equal to 20. Okay, question. Okay. All right, so moving on, we have a word problem, right? So this is chapter 3 or page 329, section 3.5. And for this problem, we are looking at maximizing the area. So we did, if you remember, we did the rancher example in class last week. So this one is, we want to maximize the area. The company plans to enclose 3 parallel rectangular areas for sorting returned goods. The 3 areas are within one larger rectangle area, and there's 1,200 yards of fencing available. So what's the largest area that can be enclosed? Okay. So unlike last week, we don't have water as one natural barrier. So we have to use part of our fencing for both of the long sides, and then we need 4 of the shorter sides, right? So we have 2 lengths and 4 widths to get that how we want it. Okay. So the perimeter, let me get a different color. The perimeter is really just adding up all of the sides. So we have 4 x's plus 2 y's, and that has to equal 1,200. Okay. But we want to get this in one variable. So let's get this y equals to something. So this would give me 2y equals 1,200 minus 4x. So y is equal to 600 minus.
Professor,
Yes.
I'm so sorry. Why is it 4x if it's just the outside?
Well, because we have to build fencing for all 4 places. Right? So if I only have 1,200 yards of material and I want to build this structure, I have to have the fencing material cover all of these paths. So it means I need to have the material cover here, 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 as well as the 3 long ones. I mean, the 2 long ones.
Okay, because when it said perimeter, I was just thinking like only the outside, but we have to account for all the material we need. Okay.
Correct.
Sorry.
Now, area is just the length times the width. Perimeter is, if you think about perimeter, like, like in the old movies where somebody's in prison or whatever, and they're like, oh, I walked the perimeter today, right? Means they go out and they just walk the fence line to cover the whole area. That's what that kind of is, right? It's like if I were to walk this area, how much of that is there, right? Whereas the area is going to cover, like if you're talking about the square foot of your house or things like that, that's the area, because it's not only the outside walls, but it's also all of the space inside and in between the walls.
Okay, that makes more sense. Thank you.
Uh-huh. All right. So now that we have that in one variable, we know that one thing to keep in mind is if I have 1,200 yards of material and I divide that only by the x's, that means that the x's have to be greater than or equal to 0. So my x is going to be, it needs to be greater than 0, but it'll have to be less than 300. And if it's 300, it can't be 300 either, because then there's nothing left at all for y. And so this is how we know that our x variable has to be somewhere between 0 and 300. Okay. So now I want to look at the area. So now to look at the area, that is my length times my width. So that is going to be my length. So x times y. So x and my y is really this 600 minus 2x, right? So I'm just substituting that in over here. Okay, so this would simplify to 600x minus 2x squared. So when I take the derivative of that, that is 600 minus 4x. So I can set my derivative equal to 0 for my critical value. And I get 600 minus 4x equals 0. So x equal 150 is a critical value. Okay. Let's look at our second derivative. Our second derivative is going to be just the derivative of our derivative, which is -4. Which that is less than 0. So I have this maximum at 150, at x equal 150. Okay, so when x equals 150, my y equals 600 minus 2x, which is 600 minus 2 times 150. So that equals 300. Okay. When I evaluate my original function at 150, that gives me 600 times 150 minus 2 times 150 squared. And that will give me 45,000 yards squared. Okay. So my maximum area will be 45,000 yards squared. And that occurs when I have a fence that is 150 yards by 300 yards. Okay. Questions? Okay. Out of 3.6, page 341. For this problem is worth 5 points. Did I put the points on this one? This one is 10 points. Okay, so for this one, problem number 8, we want to find the change in y for the given x and the change in x values. Then we'll want to find dy equals f prime of dx. And we want to find dy for all given x and dx values. Okay, so part A, we want f of x plus change in x. So that's f of x is 8 plus my change in x is 0.5. So that's f of 8.5. Okay, so that is 2 times 8.5 minus 3. So that is 14. Okay, so our f evaluated at x plus the change in x is 14. So now let's look at just f of x. So that is evaluating our function at just 8. And so that is 2 times 8 minus 3, which is 13. Okay. So our change in y then is really just f of x plus change of x minus f of x. So that is 14 minus 13, which is 1. So part B then asked us to take the dy dx equal to 2, and it wants us to really, all we're doing in this case is we want to move this to the other side, and so we're left with dy equals 2 dx. Okay, and keep in mind that dx is really just the change in x. So when we substitute in part C, we can say dy equals 2 times 0.5. And so dy is equal to 1. Okay, question. This next problem is worth 5 points. This is getting into the material that we covered this evening. So we want to determine the elasticity. Is it elastic, inelastic, or maximized? And then if it's not maximized, when will it be maximized? So our derivative is equal to -1. So to determine the elasticity formula or function, that is negative x d prime of x over d of x. So this is negative x times -1 over 500 minus x. And that equals x over 500 minus x, simplified. Okay. Part B, we want to determine at x equal 38, are we elastic, inelastic, or maximized? And so we take 38 over 500 minus 38. That equals 19 over 231, which is less than 1. So we are inelastic. So it's important that you guys remember to write whether it's elastic or inelastic on the exam so you don't lose any points on that. Okay. And then number 5, we're going to set our numerator equal to our denominator to see where we're maximized. So that's x equals 500 minus x. So that's 2x equals 500. Therefore, x equals 250. So the revenue is maximized at $250. Any questions? Okay. So the last two are where we're differentiating implicitly. So this one, we first take dy dx of both sides. D dx of x cubed. Now we take the derivative. So the derivative of y to the 5 is 5y to the 4. It has a y, so we have to add the dy dx. The derivative of x cubed is just 3x squared. We want to isolate the dy dx, so let's divide both sides by 5y to the 4, And so we get dy dx is equal to 3x squared over 5y to the fourth. And that's all there is to that problem. It'll be worth 5 points. Okay, questions? Last one, worth 5 points as well. And so this one is we're differentiating as we did in the previous one, and then we're determining the slope for the point that is given. So d dx of x cubed plus d dx of 2y cubed equals d dx of 6. So we can bring that 2 to the outside out here. And this gives us 3x squared. Now we can plus 2, take the derivative of y cubed. That is going to be 3y squared. And we have to add the dy dx on there. Okay. And then for the constant over here, that derivative is 0. Okay. Finally, we need to move the 3x squared to the other side. And so this gives me 6y squared dy dx is equal to negative 3x squared. Okay. And lastly, let's move, divide both sides by the 6y squared. So we end up with dy dx is equal to, and so this is 6y squared. So we can simplify that here. We have negative x squared over 2y squared. Okay. And the last thing we need to do for this one is the slope. It asked us, excuse me, the slope at the point 2, -1. So we would say dy dx is equal to negative 2 squared over 2 times -1 squared. So this is -4 over 2 times 1, so -2. So the slope at that point would be -2. Okay? Questions? All right. If you guys don't have any questions, that is all of the material you can expect to see on your exam. If you have any questions, happy to stick around. Otherwise, you guys are free to go. And again, no lecture next class period, as you guys will have that ability to take the exam during that time if you so choose. Okay? All right. If you don't have any questions, you're free to go. Otherwise, I'm happy to stick around and answer any questions you might have.
Thank you, Professor. Have a good night.
You too. Thank you.